Hey everybody, welcome to mini lesson number 1. This is graphing derivatives from the original graph. I'm also going to talk about how to draw an original graph from a derivative graph, but that's not quite as important right now. This corresponds to sections 2.1 and 2.2, so some of the stuff we do at the very beginning of the year. I'm not going to get into how to do a derivative or how to calculate it, because we'll talk about that a lot in class. But in my experience, the problems that people have the most trouble with are the graphs. So we're going to focus on that with this mini lesson. How do I graph a derivative graph from an original graph? Well, we talked about it in class, but here's some extra helpful hints. Okay? The first thing I want to do is find all the extrema, the max and the mins, and any other horizontal tangent, places where the graph does that, for example, or it's flat, for example. These are going to be zeros on our derivative graph. I also want to recognize any corners, cusps, vertical tangents, or asymptotes on the original graph. Asymptotes and vertical tangents, you know what an asymptote is, but a vertical tangent looks like this. It's like a sideways horizontal tangent, so that's a vertical tangent. Will be asymptotes on the derivative graph. Corners and cusps will be jumps, but those are extremely rare. In fact, I can't think of a single problem on an AP test that I've seen like that. We're going to classify the original graph as increasing or decreasing. Then we're going to label each section based on the x values. On the derivative graph, we're going to plot the zeros that correspond to any of the horizontal tangents. And then we're going to use our increasing, decreasing intervals, and we're going to connect the zeros. If it's increasing, we're going to graph above the curve. If it's decreasing, we're going to graph below. These are not exact graphs. These are only sketches. They give us some idea of what the graph looks like, and it helps you realize what derivatives really mean. So let's start off with this. Here's an original graph. It is a parabola. So let's sketch its derivative. Okay? The first thing I'm going to look for is any horizontal tangent. Any place where the graph is flat for one instant. Here is a horizontal tangent at x equals -4. So on my derivative graph, I'm going to put a 0 on -4. That's my only horizontal tangent. So now I need to figure out where my graph is increasing and where my graph is decreasing. Well, it's decreasing on the left side. It's 0 right here, and then it's increasing on the right side. So I'm going to graph a derivative graph that is below the x-axis, at 0, above the x-axis. So what shape is below 0 and then above? A line. That is your derivative graph. Okay? Let's try another one. Again, I'm going to find all the horizontal tangents I can find and plot those as zeros on my derivative graph. So I see a horizontal tangent here at 1 and a horizontal tangent here at 5. So those are places where the slope is 0. So I'm going to put a dot here at 1 and a dot here at 5 to represent the places where my slope is 0. Now I'm going to classify my graph as increasing or decreasing. Well, it's increasing until you get to 1, and then it's decreasing from 1 to 5, and then it's increasing after 5. So when I draw my derivative graph, it has to go above for increasing, through the 0, below for decreasing, through the 0, and above again for increasing. So what kind of graph goes above 0, below 0, above? It's a parabola. Again, that's not an exact graph. I don't know how tall or how low or how high this parabola goes. I just sketch a graph of it. Give me some idea of what's going on here. What is the degree of the original function? It's third. What's the degree of the derivative? It's second. What's the degree of the original function? Second. What's the degree of the derivative? First. Let's take a look at this one. This is a difficult one. What is this? Well, it's a cubic, but it doesn't go down. In fact, there are no horizontal tangents. So it will never touch the x-axis. So let's take a look at this graph and see what it's doing. It's increasing, and it's increasing, but here it's kind of increasing less. This is a really hard thing to see. It's a cubic, so going on what we did last time, if it's a third degree problem, its derivative has to be second degree, so it's going to be a parabola. It's a parabola that never touches the x-axis and is always above the x-axis. Okay? But if you notice, this point right here is where it has the lowest slope, the flattest slope. It's not quite flat, it's just flattest. So that's going to be the minimum of my parabola. I don't know where it is, but I know it's positive, and I know my graph looks like that. Now, is that an exact graph? No. You could have put the dot here, up here, anywhere you wanted to, as long as it was at x equals -6. Okay? Why does it not ever touch the x-axis? Because there's no horizontal tangents. Why does it never go below the x-axis? Because there's no decreasing part in my original graph. What degree is this? It's fourth. It's a quartic. So, based on our previous experience, what can I expect the derivative to be? Third degree, cubic. So, I'm going to go through and find my horizontal tangents. 0 there, it's a 0 there, and a 0 there. So, I'm going to put a dot here, a dot here, and a dot here. Let's figure out increasing, decreasing. It's increasing, decreasing, increasing, decreasing. The increasing and decreasing corresponds to above and below on the derivative graph. So the graph starts out above, 0, below, 0, above, 0, below. So above, 0, below, 0, above, 0, below. It's a third degree. This can be difficult. If it helps, try some more practice problems from the book or come talk to me. This is one of the most difficult topics for people to understand about derivatives. Oh, let's take a look at this one. This is an interesting graph, and it's an absolute value. It's interesting because of this point right here. This is not a horizontal tangent. It's not because it doesn't gradually change slopes. It changes slopes immediately at 3. Let's just talk about the slope of this thing. Well, the slope on this side, I'm going up 1 over 1, up 1 over 1. The slope on this side is 1. How about over here? Over 1 down 1, over 1 down 1, over 1 down 1. This slope is -1. So on this side, my slope is always -1. On that side, my slope is +1. But what about right here? Is the slope -1? Is it +1? Is it 0? Well, you better know that that's a corner, and corners don't have derivatives. So when I go to do my graph, on the left side, I'm going to have a slope of -1 until I get to this point. Open circle, because that corner doesn't have a derivative. On this side, it's going to be, open circle, +1. Now, why is that? Why do I have 2 lines? Because the graph isn't a curve. It's 2 lines. So the derivative graph is just the slope of those 2 lines. Now, let's work backwards. Going from the original graph, or getting an original graph from a derivative. This is much more difficult. The thing to keep in mind is the derivative is the slope of the original graph. If the derivative graph is above, then the original graph is increasing. If the derivative graph is below, the original graph is decreasing. Any 0 on the derivative graph is a horizontal tangent, and in some cases an original point is given. If not, you may sketch any graph that satisfies it, just like we did with the derivative graph. And there's an infinite number. You can do this an infinite number of ways. Let's take a look at this one. This is the derivative graph. Let's work backwards to get the original graph. Well, this is a 0, which means that my original graph has to have a minimum or a maximum or some sort of horizontal tangent there. This part is below, which means that it's going to be decreasing. This part is above, which means it's going to be increasing. And that dot represents a maximum or minimum. Well, use some common sense. If the graph is decreasing and then increasing, decreasing and then increasing, what shape is that going to be? It's a parabola, and that point right there is going to be a minimum. Decreasing to that point, and then increasing. Now, I could have drawn this parabola up here, I could have drawn it down here, I could have drawn it on that dot, I could have drawn it anywhere up and down through here, as long as that 6 represents the minimum of the parabola. Let's take a look at this. Now the original graph is a parabola. I'm sorry, the derivative graph is a parabola. So let's work backwards. Well, this is above, so this means it's going to, the original is going to be increasing. That's going to have a horizontal tangent. All of this is below, so this is above, which means it's increasing. This is below, which means it's decreasing. It's going to have another horizontal tangent. And again, it's above, so it means it's increasing. So my original graph has to be increasing, flat, decreasing, flat, increasing. Increasing, flat, decreasing, flat, increasing. Doesn't matter where you put these points. So I'm just going to put a point here and a point here. But they have to match up. Oops, I missed it. No, that's right. They just have to match up. So it's increasing to there. Hold on. Increasing, flat, decreasing, hold up. Increasing, flat, decreasing, flat, increasing. Again, it doesn't matter how you draw it, as long as it's increasing, 0, decreasing, 0, increasing. You could have drawn it any way you wanted to. Maybe you want that point way up here and that point way down here. It's okay. It does not tell you how to draw it. This is the trickiest one, probably. Remember, this is a derivative graph. So let's work back to the original. This is below, which means it's decreasing. It's 0, so there's a horizontal tangent. It's below again, which means it's decreasing. It's 0, so it's a horizontal tangent. And then it's above, so it's increasing. So my graph has to go down, flat, down, flat, up. That's different than every other one we've done. It's going to go down, flat, down again, flat, up. So I'm going to put a point somewhere here and somewhere over here. Again, where you put the points doesn't really matter, as long as your graph goes down, flat, at -7. Then it's going to go down again, and flat, at 1, and then it's going to go up. This point over here is a minimum. You can see that. It's a minimum because the slope went from a negative slope to a positive slope, from a negative slope to a positive slope. What about this point? It's not a maximum or a minimum. Why not? Because the slope was negative and negative. It didn't change directions, so it can't be a max or a min. It's still a horizontal tangent. It's still flat, but it's not a max or min. Let's try this one. This is always one of the most difficult problems. I'm going to sketch a graph with the following characteristics. First of all, the graph is continuous. That doesn't really help me right now. F of 1 equals 3, and f prime is this piecewise function. Well, continuous doesn't really help for the graph. F of 1 equals 3 is a point. The point is 1, 3. So I have a specific point to start with. Now let's talk about the derivative. What is the derivative on a graph? What does a derivative look like on a graph? These are slopes. And it's going to change slope. Where is it going to change slope at? It's going to change slope at at 5. So I'm going to come over here and I'm going to put a little dotted line here at x equals 5. Now I know that looks like an asymptote. It's not an asymptote. It's just there to remind myself that when I get to 5, I need to change slopes. Well, I know this dot has to be on the graph. Is this dot on the left side or the right side of my break? It's on the left side. Which of these two is on the left side of 5? This slope is on the left side of 5. So I'm going to start at my dot and I'm going to do a slope of 3/2. That means up 3, 1, 2, 3 over 2 and put a dot. 1, 2, 3 over 2 and put a dot. And I'm going to stop right there. I could also go down 3 and back 2. And draw my line. Now, from that point, I have to change slopes. What slope am I going to change to? -1/2. That means down 1 over 2, down 1 over 2. It's going to look like that. So again, this slope is 3/2 from this starting point. This slope is -1/2. Now the one thing we didn't talk about is the graph continuous? It sure is. If I did not have this rule right here, I could have this line here, and then I could have this part down here like this. But because the graph has to be continuous, I can just keep going from the point that I stopped at. If you guys have any questions, come talk to me. Otherwise, thank you for watching.